All right, welcome back to chapter 5. We are going to apply this electronegativity, this polar covalent bond to the molecule as a whole. So this video is going to be very thick, very heavy, but it's an important skill that we need to learn moving forward in chemistry. All right. So up until this point, I'm going to assume that you can draw a Lewis structure. I'm going to assume that you can determine the geometry of a molecule and that you can start to see that geometry in 3 dimensions. So you can see what a BET molecule looks like in your mind. I'm also going to assume that you have had a little bit of practice with determining the type of bond. So is it a polar covalent, pure covalent bond? So subtracting those electronegativities and determining the type of bond. So those are all the skills that you're going to need to have as we work through this video. So ultimately on an exam, I'm not going to ask you, is this bond polar covalent, or what kind of bond is this? What I'm going to be interested in is this molecule a polar molecule? So what we're going to start to do after this unit is we're going to start to see how these different molecules interact with one another. So if I put 2 different types of molecules into a beaker, well, how do those 2 molecules interact with one another? So one of the things that we're going to need to know is it a polar molecule? So that's what we're going to focus this video on. All right. So to do that, there's a couple of things that we have to keep in mind. We've got to look at the individual bonds. So first, we're going to look at the individual bonds and determine, well, is there a dipole moment? Is there a moment where these the electrons or the charge is separated? And then the other thing we have to look at is, what does that molecule look like in 3 dimensions? Is it pulling in equal and opposite directions, or is it pulling to one portion of the molecule while the other portion is left without? So those are the 2 things we're going to have to consider. Is there a dipole moment to begin with? And if there is, what does the shape of that molecule dictate? So the first one that we're going to answer is water. So is water a polar molecule? So the first thing we're going to look at is there a dipole moment? So just as a reminder, water is H2O, of course. So this is going to be oxygen, hydrogen, hydrogen. So to determine if this is a polar molecule or not, we have to determine or look at how these bonds or electrons are shared. So what we're going to do is we're going to isolate one of these bonds. So I'm going to look at oxygen and I'm going to look at hydrogen. So let's say I isolate this bond right here. Okay, I'm going to see, is it a polar bond? All right, so oxygen, the electronegativity for oxygen is 3.5. Hydrogen, the electronegativity is 2.1. Separate that, and I get an electronegativity difference of 1.4. With an electronegativity difference of 1.4, what kind of bond is that? It is a polar covalent bond. So oxygen bound to hydrogen is a polar covalent bond. There is a dipole moment. Who is big brother and who is little brother? Oxygen is big brother, so we have a partial negative here, partial positive by the hydrogen. Okay. Well, notice that there is more than one bond on this molecule. Okay, so there's this other bond over here, right? Well, it happens to be the same atoms, but we treat it as a completely separate entity, as a completely different side. So this is also a polar covalent bond. Hydrogen is still the little brother. Oxygen is still the big brother. So we still see a push towards the oxygen. Okay. All right, so first thing, is there a dipole moment? Is there a separation of charge? Yes, there is. These electrons are not being shared equally. So now we need to take a look back and look at the molecule as a whole. Okay. So if I were to draw those dipole moments onto this molecule, what would it look like? Well, this dipole moment is pushing from the hydrogen up towards the oxygen. And this dipole moment is pushing up from the hydrogen towards the oxygen. So if I were to add these together, I would see a region up here at the top that is very electron rich. So there would be a lot of negative charge or feel up there. And down here at the bottom of my molecule, it would be a very electron poor. So this molecule as a whole does have a separation of charge. Up above the oxygen is going to be electron rich. Down below the hydrogens is going to be electron poor. So is water a polar molecule? Absolutely it is. There is what we call a net dipole moment going from the bottom of the molecule up through the top. Okay. And we see the same thing here. So electron rich on the top, electron poor on the bottom. What about ammonia? So go ahead and pause the video and see if you can determine, is ammonia a polar molecule? And if it is, what does it look like? Where's those polar regions? Okay. So step one is isolate the bonds and see if there is a dipole moment. So I'm going to isolate this nitrogen-hydrogen bond. Okay. So electronegativity for nitrogen, and again, it'd be helpful to have that chart in front of you at this point. But nitrogen is 3.0. And hydrogen is 2.1. So electronegativity difference is 0.9. That falls in the middle region. That falls in our polar covalent bond. So there is a dipole moment. There is a big brother and a little brother. There is a separation of charge. Okay. So looking at just this isolated bond, what does that dipole moment look like? Big brother, little brother, pushing towards the nitrogen. Okay. So then we would do this for each of our other bonds, right? So we would isolate this bond, look at the dipole moment, and we would isolate this bond, look at the dipole moment. All of those are hydrogen-nitrogen bonds, so all of those do have a dipole moment. Now we need to look at this molecule in 3 dimensions. So we've decided that each of the bonds, there is a dipole moment, there is a separation of charge. So all of these are going to push towards the nitrogen. So we need to be able to identify that this would be a tetrahedral electron geometry and a trigonal pyramidal molecular geometry. So that means these are going to stand up like a pyramid, right? So we have a dipole moment up towards the nitrogen, dipole moment up towards the nitrogen, dipole moment up towards the nitrogen. So if I were to look at where we have an electron-rich region, it would be up here above the nitrogen. And if I looked at where we had an electron-poor region, it would be down here by all these hydrogens. Okay. So is ammonia a dipole molecule? A polar molecule. Absolutely it is. And the dipole is going to go up straight through that nitrogen. Okay, so right through the bottom. All right, one more. Is carbon dioxide a polar molecule? So pause the video and see what you can find. All right. So first things first, we're going to try to determine, is there a dipole moment? So I'm going to isolate one of these bonds, and I'm going to look at the separation of charge. So electronegativity for oxygen is 3.5. Electronegativity for carbon is 2.5. So the electronegativity difference is 1.0. So 1.0 falls again in the middle region. So yes, there's a dipole moment. There is a separation of charge. Oxygen is big brother. Carbon is little brother. So it's going to push out towards the oxygen. Okay. So isolate the bond on the other side. And do the same process. So again, it's still a carbon-oxygen bond. So oxygen's still going to be big brother. Carbon's still going to be little brother. And it pushes towards the oxygen. Okay. So is there a dipole moment? Yes, there's a dipole moment. Is this a polar molecule? What? It's not? Well, there's a dipole moment, so why is it not a polar molecule? This molecule is a linear molecule. It's a straight line. So the oxygen is going to pull in this direction. This oxygen is going to pull in this direction, but they're pulling in equal and opposite directions. So picture two people on the end of a tug-of-war rope that are exactly the same strength. They pull and pull and pull and pull, but is the middle of that rope going to go anywhere? No, it's not, right? So these oxygens are pulling and pulling and pulling on these electrons, but they're not actually moving to one side of the molecule or the other. They're staying put right where they are. So carbon dioxide is a non-polar molecule because it's pulling in equal and opposite directions. Okay, so there would be no net dipole moment. So what this tells me is that there's a lot of things to consider when looking at the polarity of a molecule. So what I'm going to do now is I'm going to lay down a very basic list of rules. This list of rules is not all inclusive. There certainly are going to be exceptions to the rule later in the chapter, but this is going to give you a good starting point, a good place to start organizing your thoughts as you move through these problems. Because I know there's a lot of things to consider as you're moving through these problems. Okay? So there's going to be two questions that we need to ask ourselves when we're trying to determine the polarity of a molecule. Okay? So is this a polar molecule? That's the ultimate question. Okay. So one of the things we're going to have to consider is there a dipole moment? Okay. So this has to do with looking at two atoms, looking at their electronegativity difference, so isolating those bonds. So if the answer is no, there is no dipole moment, they are sharing electrons equally, then there is no chance that it is a polar molecule. So no dipole equals not polar. Okay? If the answer is yes, there is a dipole moment, there is a separation of charge within one of the bonds or all of the bonds. So yes, dipole, then it may be polar. That doesn't automatically give us a yes, a dipole, yes, it's polar. We saw that with carbon dioxide, right? There was a dipole moment, but there wasn't a polar molecule, okay? So what that does is it kind of leaves us in the running. It gives us the option to continue looking at this molecule. So we get a no, shut it down. We get a yes, we keep moving forward. Okay, the other question that we have to ask ourselves is about the shape, right? So does the shape lend itself to being a polar molecule? And this is a very, very basic way to think about it. There's certainly exceptions to the rule, but it's a good place to start. So just know that this is not all-inclusive, but a good place to start. So the question I ask is, are there any lone pairs on the central atom? Okay. So again, are there any lone pairs on the central atom? If the answer is no, no lone pairs equals not polar. Okay. So if we look at this example here, we see carbon as the central atom. Are there any lone pairs on that carbon atom? No. So no matter what happens between these two bonds, they will always pull in equal and opposite directions. So let's say the central atom is something like this. So sulfur with 3 oxygens around it. Okay? Are there, and it's actually going to look like this, are there lone pairs on that central atom? No. So this will always be a non-polar molecule. So even if there's dipole moments here, these guys, remember, are all 120 degrees away from each other. So just think of it as a 3-way tug of war. They're always going to pull in equal and opposite directions, so that rope in the middle is not going to move anywhere. It's not going to, the electrons aren't going to move anywhere because they're pulling equal and opposite, or they're pushing equal and opposite, whichever way. Okay. So, are there lone pairs on the central atom? If the answer is yes, lone pairs, again, it may be polar. Okay? So in this case, we've got to have 2 yeses in order to have a polar molecule. If you look at either one of these questions and the answer is no, shut it down, okay? So is there a dipole moment? Yes. Are there lone pairs? No. Shut it down. We got to know. Are there lone pairs? Yes. Is there a dipole moment? No, they're sharing electrons equally. Shut it down. So if the answer is no to either question or both questions, shut it down, not polar. You have to have a yes and a yes for this to be polar. So let's look at water. So is there a dipole moment? Yeah, we determined that there was in fact a dipole moment between hydrogen and oxygen. So we got a yes. Are there lone pairs on the central atom? Oh yeah, there are. So we got another yes. A yes and a yes. And this was a polar molecule. So certainly there are exceptions to these rules, but start here. As you get more proficient, as you start to picture these in 3 dimensions, as I start adding things to atoms that may not be the same atom on every side, of course, this is going to start to break down. So would these guys pull in equal and opposite directions? Well, they'd pull in opposite directions, but it's not necessarily going to be equal. So there certainly are some things to consider outside of these two, but this is a wonderful place to start. So go practice this skill. For those of you that are taking 152, I open up 152 with polar molecules. So it's not going away. Okay. So I hope you guys found this helpful.